I want to have a model of where people live. And I'm going to think of a very simple world. There's a city. It's here. And then people decide where they're going to live. There's just a road that runs through this city. And I want to make it just a linear road to make my life easy. And you have to decide how far from the city you're going to live. And I'm going to let t equals the travel time per day of a location. So that's your daily travel time. Assume everybody works in the city. So you have to go to the city and back, and t is the total time it takes you to get to the city and back from a given location. Okay? And I'm going to let r of t equals the rent that you pay to live at t. Okay, so to live at a location with distance t, you got to pay r of t. All right? So presumably we would think r prime of t ought to be less than 0, right? That is, rents ought to go down if you have to travel further, right? That's going to be kind of a simple implication. Everybody would prefer to have less travel time. So in equilibrium, you're going to have to reward you for traveling farther by giving you cheaper rent. That's going to be this model. Okay? And what we want to know is, what can we say about this rent function? What is it going to look like? And I want to think about a very simple model. I want to think about a model where people care about two goods, consumption and leisure, right? The standard labor supply model economists use. And you'll notice one thing interesting in this model. Even though I'm interested in this problem of where to live, I didn't put where to live in the utility function. Okay? That's going to turn out to be important. I'm interested in where you live, but I didn't put where to live in the utility function because I'm saying people don't directly care about where they live. They only care about where they live because it affects their travel time, right? I put a restriction on preferences. I've simplified their preferences to say, no, people don't have some preference over how far to travel. All they care about is consumption and leisure, but the problem with travel is it takes away from your leisure. That's the basic idea. Okay? So I'm going to think about this person's budget constraint as being C equals, let's say, 24 minus L minus T. So this is how many hours I have in a day. That's how much leisure I take. That's how much travel time I have. So that's how many hours I get to work. That's my working hours. Times W minus R of T. All right? That's how much I get to consume. I get to consume my hours worked times my wage minus however much I could pay in rent. That's what I have left to consume on this other good. Everybody understand that? So everybody has to find a place to live. Once they find a place to live, they have to work, take so many hours out of the day, they have to travel, whatever's left they get for leisure. So that's their budget constraint. Okay? All right, everybody understand this? So the Lagrangian for this problem L equals U of C comma L plus lambda 24W minus LW minus TW minus R of T minus C of T. Right? That would be my Lagrangian, because that has to be equal to 0. Just move the C over the other side. So what are my first order conditions? First order conditions, partial U, partial C equals lambda. Not very surprising. Partial U, partial L equals lambda W. Also not surprising. Those are the usual labor supply first order conditions, right? Lambda is the margin utility of consumption. I go to the point where the margin utility of leisure is equal to the margin utility of consumption times the wage rate, because that's what I get for working more. So nothing unusual about that part. What about T? What's the first order condition for T? Well, differential respect to T, I get lambda minus R prime of T minus W equals 0. So lambda doesn't matter. So I get W equals minus R prime of T. It says I'm going to choose the place to work where the savings I get in rent from leaving another hour further is equal to the wage rate. Right? Why? Because for every hour I spend traveling, that's an hour I could have spent working. So the opportunity cost of my time is W. So if by traveling an hour I can save more than W, then that's better than work. If by traveling another hour I can save less than W, I'm better off moving closer to work and spending an extra hour at work. Right? Because the guy views, in this model, the key assumption, he views riding in the car as the same as working. They both take away from his leisure. We've made the restriction that travel and work are really the same thing. And the price of work, therefore, becomes the price of travel. And therefore, the choice of where to live is really a production decision. It's not really about a consumption decision. It's effectively a decision over where you should work. Should you work by driving your car, or should you work by working at work? They're both work, right? One, you're driving. One, you're a limo driver with one passenger. The other one, you are working at work. And it's saying when R prime is bigger than W, or minus R prime is bigger than W, it says the wage of being the limo driver exceeds the wage the guy's paying me at work. So I'll spend more time driving the limo and less time working at work. Right? You can see the problem? You're basically working in the car. Right? That's the way to think about it. All right? Now, what's the implication? So what does this mean? What is the rent curve going to look like in this world? So let's think about it. Here's T. What's the rent curve going to? Who's going to live closest to the city? Yeah. Highest wage worker. So there's going to be some rent in the center of the city. R of 0. Right? That's the rent you pay with no travel. The slope of this curve at this point is going to be equal to what? The wage of the highest wage worker. Right? Everybody agrees with that. Right? The slope at that point, slope equals minus W max. Right? The slope at that point is the maximum wage worker. Right? The highest wage worker slope is going to determine the slope at that point. As we move out from the city, what's going to happen? Who's going to live a little further out? Well, it's going to be someone at a little lower wage. And the further I go, the lower the wage is going to be. So this curve is not only going to be downward sloping, it's going to be convex. Because the slope is getting smaller and smaller the further out I move, because the wage rates of the guy who lives there is getting lower and lower as I move out. The more inequality there is, the more convex it'll be. Right? Everybody understand that? All right. Now, that determines the shape. So once I know R0, in fact, all I would need to know is the wage distribution, and I could just draw this whole curve, right? You can see how powerful this theory is. It has very, very strong predictions. That is, once I know the wage distribution, I can predict without knowing anything else what this curve is going to look like. Not just qualitatively, quantitatively. I can just say, okay, start here. I know the slope. I know it's just a differential equation that says the slope of the curve at every point is equal to the wage of the guy who lives there. And the guys who live there are ordered from the highest wage to the lowest wage. Doesn't matter their preferences. Some guys could have preference. U doesn't show up anywhere in this calculation. Right? No, I don't care. I mean, it doesn't matter what this thing looks like. As long as they're commuting to work, I got this equilibrium. All right. Question or? Okay. All right. What? Yeah. R prime is the slope. R prime is the slope. Right? Because W is not the height of that curve, it's the slope of that curve. Now, one thing I haven't determined is how do we get R0? I haven't yet figured out how to do the boundary condition. I got all the indifference conditions because that's my indifference condition right here. I haven't figured out my boundary condition. How are we going to close this model and get a boundary condition? No, that just determines the slope, right? Even if I knew that, that just determines the slope. It doesn't determine how high R0 is. Right? You can see why that doesn't determine R0. R0 is not determined by how big W is. All right? Well, the answer is, think of the following. At some point, I'm going to run out of people. Right? They're going to crowd as close to the city as they can. And I'm going to keep piling the people, and I'm going to get out there. And at some point, I'm going to get the lowest wage guy, and he's going to live there. He's not going to want to live any further because there's no reason. It'll be an empty house, and he's moved back. All right. All right. So now what's the rent going to be at that point? 0? Well, depends on what this land has to compete against. The most simple model, we think like there's some agricultural use of the land that doesn't care about being close to the city. Think about there being some R bar, which is land used to grow wheat or corn or whatever raise hogs, whatever the alternative is. And for simplicity, I assume it doesn't depend on T. It's okay if it depends on T. I'll just make it flatter in T than this, right? That's all I need. That this is that the boundary with the outside market is out here. All right? All right. Yes? Not anymore. Now we know everything. That's what I say. That's all you need to know. If I told you the wage distribution, now think about, now that I've introduced R bar, I would say to fit all the people, I got to go out this far. All right. So I know the rent when I run out of people, call that T max. Okay. At the maximum T point, I know R bar has to be the wage. So R of T max equals R bar. Then I know the slope there has to be equal to the wage of the lowest wage guy. And then I just start following my differential equation up that curve until I get to the center of the city. And at that point, I got the rent in the city. No, we didn't assume that. We did not assume that they lived closer to the city. No, that's a prediction of the model, right? We didn't start by we didn't say, well, let's assume they live closer to the city. No, in this model, they will live closer to the city. they gain more from living closer. So they will live closer, right? This is really critical that you understand that we didn't make that wasn't an assumption. That was a prediction of the model, right? This model predicts they will live closer to the city. We didn't start with that assumption. We didn't have to say, well, if they live closer to the city, this will be the equilibrium. We said if they can live wherever they want, this will be the equilibrium. If they possible, they could live in the reverse order if they wanted, or randomly if they wanted. They can do whatever they want. But in equilibrium, this is what they will do. They will sort themselves, just like our earlier people sorted themselves between the A's and the B's. These people will sort themselves out with the higher wage people living closest and the lowest wage people living furthest, and the rents will be determined according to this formula I just wrote on the board. Okay? Yeah. Well, because I just assumed it was uniform. Then it doesn't matter where it runs out. If there was an alternative, if you made this alternative like sloped, I don't know, it doesn't matter. Just where those curves cross would be where we'd end up. The fact that this is uniform is just for simplicity. What? No. There's no level of wages that's related to R. W is the slope. Oh, then those people would not have a house. It seems like we kind of assumed that we run out of people before that. Yeah, I mean that's yeah. So what if we didn't? What if we didn't? What if we ran out of? What would happen if I ran out of willingness to pay before we got to that point? Then what would happen? Then we would start at some point. There would be some W min, which would be the minimum wage guy who's willing to pay R bar. We would then follow the curve from that point in. It would look just like this picture. It would just follow the curve from that point in, right? Right? We'd still start at R bar. You agree with that? Yeah. And we would still use the wage of the guy who lives there as the wage rate. And we would just follow our way into the city. Yeah, then they would be irrelevant for this purpose, right? They would basically not determine the they wouldn't determine the rent gradient because they're out of the housing market. Yeah. No. The price has to be the same. Because the guy who lived 9.7 miles from the city is indifferent between that and living 9.71. They can't be a jump. No, because you always run out of people at R bar. Well, I mean, now you're just assuming it's not continuous. If there's a continuum of people, the last guy you're going to be at R bar. You cannot have this equilibrium, right? You cannot have this land and then the prices jump up to here. Why? That cannot be an equilibrium. Because the guy who lived here would say, hell, I could live a nanosecond further from work and pay a lot less in rents. That could never be the equilibrium. Right? Because the guy who lived right there at the end would be stupid. He'd be saying, I could live a nanosecond further and pay a discretely lower rent. That couldn't possibly be the equilibrium. No matter if there were 1 million homeless people, right? The number of homeless people had nothing to do with that argument. It's about the guy who was paying the rent that would prevent that from happening. You get the idea. That's why you can't get the jump. What? No, if the landlord, these landlords would say, come live at my house and I'll get rid of the pigs, right? I'll throw the pigs out and you can live there. No, he can't, because the guy next to him would throw his pigs out. Think about it, all right? All right, well, so let me give you some examples. Think about some comparative statics to make sure we understand the model. What would happen if I raised the wages of low-wage people? That's all I did, just made low-wage people's wages higher. Didn't increase the number of people, nothing. What would happen? It would change the slope out here, but then it wouldn't change the slope from that point forward, right? It would make it steeper where I raised wages, but then the slopes would be the same, so rents would go up throughout the distribution. Okay? What would happen if what would happen if I came in and raised the wage of only the top half of the distribution? What would happen? Yeah, there would be no change because I haven't changed R bar. I haven't changed the rent out here. And because the boundary condition is out here and the indifference relationships are working off that going toward the city, the only effects would be to the left of the point. So if I started increasing wages with this guy right here, we'd become steeper in this range. That's all that would happen. Okay? People understand that? We'll see how that works. What if I raised inequality holding the average wage fixed? What would happen? What would happen to my equilibrium if I held the average wage fixed? So I have this initial equilibrium. What would happen? Well, if I'm holding the average fixed in the sense of holding the average weighted by time from the city, right? This just sort of thought about keeping the same average slope over that whole period, right? Then what would happen? Well, it would become flatter out here. It would become steeper over here, but it would end at the same point because it would have the same average slope. So, interestingly enough, that would have the effect of lowering wages everywhere, lowering rents everywhere, right? Rents would fall out here because it's flatter, and then they would be equal only when they reach the center, where in fact that average would be the same as it was before. The reason is because at each point, the rent that I pay is determined by the wages of the people who live further than me outside the city, right? That's how my rent's determined, by what they're willing to pay, okay? And because my rent is determined by what they're willing to pay, and their wages have gone down on average, right? Because everybody below me's wages gone down on average, while everybody above me's wage has gone up on average. Therefore, it must be that my rent would have to go down, being this simple model. Right? Now, the average is an interesting average. It's an average kind of weighted by distance. It's not necessarily. Now, if everybody lived along a line and everybody traveled the same distance, then it would be just, if they were the same distance apart, then it would be the usual average. If it was like everybody lived on a circle, then it would be different, because as you moved out, you get more and more people in a given distance from the city. But the basic idea is the same. You want to understand how that equilibrium is determined. Let me give you a nice practical application of this. Okay? Let's assume that poor people live in high crime areas, right? Right? Everybody agrees with that, right? On average, poor people live in high crime areas. Why? Well, there's two reasons you could say. One is they commit crime, but let's leave that one aside. Let's assume they're not the guys committing crimes. We have a separate theory why they commit crimes, but we'll leave that aside for the moment. Let's assume, why would they live in high crime areas? Yeah. Yeah, it's the safe, low crime areas are normal good. They're poor, If I'm poor, same prices that everybody else faces, I'll choose the high crime area. Okay? What if we magically came in and reduced crime in those areas? Would those people be better or worse off? They could very well be worse off, right? Because the rent that they pay would be determined by the marginal person willing to live in that neighborhood, right? The guy on the margin of living in that neighborhood. The marginal person presumably values the crime reduction more than they do, right? Because if it's a normal good, the guy who's the poorest values it the least. As that bids up rents in that neighborhood, rents would rise faster than the value to them of the crime reduction. Yes? Oh, that's the yeah. If they own the house, of course, then it's not where I live; it's where I own the property, right? It has nothing to do with where I live. It has to do with being an owner of the capital, right? So, if I owned houses in another neighborhood, I'm going to benefit, right? But the key point I'm trying to make here is that changes in the marketplace, because market prices are determined by the marginal willingness to pay, if prices respond to a rise in the marginal willingness to pay and I value it less than they do, I might end up being worse off. So this has important implications. I remember once I went to a conference where people were talking about, like, saying, geez, isn't it terrible that all these people live in low quality housing? Wouldn't it be better if we improved all that housing? And the answer is it might in some sense, but they might be worse off. In fact, what would they do if you improved the quality of the housing? They would leave and move to someplace else that had lower quality housing where they'd be willing to pay the price. And you might think this is a theoretical possibility. This is a real world phenomenon that happens all the time. And in fact, poor people often get up in arms when their neighborhood starts getting revamped to be a lot nicer, right? They get priced out of their neighborhood. And because they don't own their own homes, they actually could easily be worse off as rents rise. And where do they move when they leave those neighborhoods? Another lousy place, right? Now, I'm not saying it's not bad to be poor. I'm just saying, they're doing the best they can with the resources they have available. But since they won't necessarily benefit from an increase in the supply of high-quality housing if it comes at the expense of reduced supply of low-quality housing. Okay? It's exactly this kind of model here. Exactly. And the rent gradient model I like a lot as a teaching tool because it really illustrates a couple important features. One is it illustrates the power you can get out of a model when you kind of make preferences very simple and you push what is a consumer choice problem essentially to become what we'll call a production problem, that it really is a cost minimizing exercise. And the nice thing about thinking about it as a cost minimizing exercise is it really gets away from the whole idea of preferences, right? The question of where to live had nothing to do with my preferences. It was all about where was the cheapest place to live, and that came down to comparing the wage cost of traveling further with the rent savings from traveling further. You could do the same thing for thinking about what kind of car to buy. You could say, well, geez, I need more space, but at the same time, I can trade that off against gas mileage, and so I minimize some cost per unit, something like that. So the more you can restrict preferences, the more you can simplify the model, the better. The more you can push it into a production problem where you can observe the trade-off. The trade-off is not something that can only be inferred from choices. You actually know the components. The better, more powerful your model is going to be, and we saw it in that case. So that's one aspect. The second important aspect is it very clearly illustrates how these kind of what we call hedonic models work. In other words, what we had was we had a situation where we were going to end up, this was travel time, remember, and this was rent. And because everybody preferred a lower rent, right? Everybody prefers, what's the preference direction on this graph? They prefer a lower rent, and they prefer less travel time, right? So the preferences are going to go in that direction. So we know the equilibrium trade-off is going to have to be downward sloping, right? You've got to get a lower rent in exchange for traveling farther. That's no problem. So every consumer is going to choose a point where they're indifferent for between moving a little bit closer. And that was what we said before. And we could say, well, geez, that meant our rent gradient had to be convex like that because the highest wage consumers would live closest to the city and the lowest wage consumers would live farthest from the city, right? So the slope at any point would have to be equal to the wage rate of the person who lived there. Otherwise, they wouldn't be maximizing, or in this case, really minimizing cost. Now, that didn't answer the question about where this equilibrium is pinned down, right? Because how do I know it's not going to be, it's going to be this curve? How do I know it wasn't a parallel curve a little bit higher? And that came down to finding our boundary condition. That is the condition that determined where these indifference relationships would start. And in this problem, the natural place to think about the boundary condition was to think about a world in which there was some backstop rent R bar that the land could earn independent of how far it was from the city. And the fact that R bar is flat as opposed to a function of t doesn't really matter. It's just, that makes it simple. So this point is going to be here. And then we used our indifference relationships to figure our way up the curve. So you can think about the central city rent as being kind of determined by kind of an indifference relationship starting from out here.